And now in this lecture I answer 2 questions. In the first question we find out there are this semicircle that is inside quarter circle A or B. In the second question we find out there are this grand shape. So let's start with the first question. In the boundary we have a semicircle inside this quarter circle A or B. This is a right angle, angle A or B is a right angle. OS equals to 30 sinus length. And we also know that RKQ is equal to RQB. Again, our task is to find out there are these semicircles. So first of all, we will define the center of this semicircle. This point is point C. We define the touching point of this semicircle with this quarter circle. This point is point P. We define the radius of this semicircle as R. CP is the radius of the semicircle. Therefore it is equals to R. Likewise, CQ is also the radius of the semicircle that is equals to R. In the next step, we'll join point C and S together by a straight line. Point S is the point of tendency of tangent OB with this semicircle. So point C is the center of this semicircle. Point S is the point of the semicircle itself. Therefore, CS is the radius of this semicircle. That equals to R according to our definition. The radius CS that equals to R. The radius CS is drawn to point S, that is the point of tendency of tangent OB with this semicircle. And radius that is drawn to the point of tendency, then tangent OB will be perpendicular to the radius SC. If OB is perpendicular to SC, it means that this angle equals to 90 degrees. This angle also equals to 90 degrees according to rule 1. In the next step, we will do another construction, that is to say from point Q, we will do perpendicular on OB. Again, from point Q, we will do perpendicular on OB. So actually, this angle equals to 90 degrees. And this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q inside OB. This point is point M. Those two angles are defined as interior angles, one-sided interior angles. The sum of those two angles is of course equals to 180 degrees. And according to rule 22, if the sum of two one-sided interior angles is equal to 180 degrees, then they are located between parallel lines. That is to say, because of the fact that the sum of those two one-sided angles is equal to 180 degrees, they are located between parallel lines. That is to say, PO is parallel to CS. So quickly on rule 22. According to rule 22, if the sum of two one-sided interrogus is equal to 180 degrees, then they are located between parallel lines. In the drawing we have line A and line B. The red line C cuts those two lines A and B, those 2 points. Those angles alpha and beta, they are defined as one-sided interrogus. So if the sum of those 2 one-sided interrogus is equal to 180 degrees, then they are located between parallel lines. That is to say, line A is parallel to line B. So the division we can implement rule 22 in our drawing, because the sum of those 2 one-sided interrogus is equal to 180 degrees, and therefore they are located between parallel lines. That is to say, PO is parallel to CS according to rule 22. Likewise, the sum of those 2 one-sided interrogus is equal to 180 degrees, and therefore they are located between parallel lines. That is to say, CS is parallel to QM. CS is parallel to QM. Likewise, the sum of those 2 one-sided interrogus is equal to 180 degrees, and therefore they are located between parallel lines. That is to say, PO is parallel to QM. So PO is parallel to QM according to rule 22. So today we found out that PO is parallel to CS and is parallel to QM. All those 3 lines PO and CS and QM, they are parallel to each other according to rule 22. Line segment QP connects between those 3 parallel lines. Okay, line segment QP connects between those 3 parallel lines. Likewise, line segment OM is also connects between those 2 parallel lines. And whenever we have 3 or more parallel lines that are connected with other 2 lines that are not parallel to each other, we can implement Thales theorem. According to Thales theorem, a special relationship exists between the 2 lines that connects the parallel lines and the 2 lines that are not parallel to each other. That is to say, a special relationship connects exists between QP and OM that are not parallel to each other. Special relationship exists between those 2 lines that connect the 3 parallel lines. And the relationship is as follows: PC over CQ equals to OS over SM. You get PC over CQ equals to OS over SM. So write it down. So according to Thales theorem, PC over CQ equals to OS over SM. it again according to Tell's theorem. Special relationship exists between line segment PQ and OM that connects those three parallel lines. That is to say, PC or CQ equals to OS over SN. PC is R, CQ is also R. This is equals to OS, that is 3 according to what is given us the question. Over SM. SM is the missing side, so we leave this it is. So in total, we should find out that R over R equals to 3 over SM. R over R is 1. So 1 equals to 3 over SM. Here we will multiply this equation by SM. And finally, we get that SM equals to 3 units in itself. This is line segment SM that equals to 3 units in its length. In the next step, we'll do another construction. But before that, we'll join points O and Q together by a straight line. And joining points O and Q together, the right triangle QOM. So we know that angle AOB equals to 90 degrees in its size. This is angle AOQ. Center angle AOQ, because of the fact that point O is the center of this quarter circle, angle AOQ is defined as center angle. This is center angle AOQ. That's subtend on chord AQ. Again, center angle AOQ. This center angle AOQ subtend on this arc RKQ. Likewise, we have this is center angle QOB. Center angle QOB that subtend on this arc RQB. And because of the fact that those two center angles subtend on equal arcs, that is to say RKQ equals to RQB. According to what is going on in the equation, they must be equal to each other in their sizes. That is to say center angle AOQ is equal to this in its size to this center angle QOB. According to rule 23. So I can check on rule 23. According to rule 23, the center angles that subtend on equal arcs are equal to each other. In the one circle, this is center angle AOB that subtend on RKB. Likewise, this is center angle COD that subtend on arc CD. So if those two arcs are equal to each other in their lengths, those two center angles that subtend on those two arcs must be equal to each other in their sizes. That is to say alpha equals to beta. So whenever you have two set triangles that subset of equal arcs, they must be equal to each other in their sides. In this case, if arc AB equals to arc CD, then alpha equals to beta. So according to Rule 23, because of the fact that those two set triangles subset on those two equal arcs, they must be equal to each other in their sides. So if we define the side of this set triangle as theta, then the side of this set triangle must be also equal to theta because they are equal to each other in their sides. Theta plus theta equals to 90 degrees because angle AOB equals to 90 degrees in size. Theta plus theta is 2 theta, so 2 theta equals to 90 degrees. 2 theta equals to 90 degrees, and therefore angle theta equals to 45 degrees in its size. This is angle theta, angle AOB equals to theta, and this equals to 45 degrees in size. In the next step, we will focus on the right triangle, triangle QOM. This is the right triangle QOM. So I'll copy. So you can see that in the right triangle QOM, this angle QOM equals to 45 degrees in size. So in the right triangle QOM, tangents 45 degrees, equals to QM over OM. Again, in the right triangle QOM, tangents 45 degrees equals to QM over OM. Tangents 45 degrees is 1, so 1 equals to QM. QM is the missing side, so limited it is, over OM. OM in total equals to 3 plus 3, that is 6. So in total, I'm sure you found out that one equals to QM over 6. Here we multiply this equation by 6. And finally we get that QM is equal to 6 units in its length. This is side QM. Is equals to 6 units in its length. In the next step, we will do a construction. That is to say, from point C, that is the center of this semicircle, we will do perpendicular on QM. Again, from point C, we will do perpendicular on QM. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the construction. we define the touching point of the perpendicular from point C and QM. This point is point L. By doing this construction, we created here quadrilateral CLMS. In quadrilateral CLMS, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the side of this 450 degrees, in total must be equal to 360 degrees according to the rule. It states that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 450 degrees must be equal to 90 degrees in its size. So in quadrilateral CLSM, we have 4 right angles. According to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle if not a square, so we write to quadrilateral CLMS as a rectangle, because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle CLSM, side CL is equal to the opposite side LM, but CS is R, therefore the opposite side LM must be also equal to R units in its length. Likewise, according to the same rule, in the same rectangle CLMS, side SM must be equal to the opposite side CL, but SM is 3, therefore the opposite side CL must be also equal to 4 units in its length. What is the length of this line segment? Line segment QL. From the drawing, it is very easy to see that QL in total equals to QM minus LM. Again, QM minus LM equals to QL. So as we know, we should find out that QL equals to QM minus LM. So total QL, let me see inside line segment QL, equals to QM. QM is 6, according to what we already found out, minus LM. LM is R. So total QL equals to 6 minus R units in its length. This is the right triangle QCL. So copy this right triangle in your page, and we'll implement the Pythagoras theorem in this right triangle QCL. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is abbreviation for Pythagoras theorem. So actually, this this is right triangle QCL, the call from the original drawing. This right triangle QCL, according to the Pythagoras theorem, QC squared, that is the square of the hypotenuse, equals to QL squared plus LC squared. So I write it down. So QC squared, that is the square of the hypotenuse, equals to QL squared plus CL squared. QC equals to R, therefore QC squared equals to R squared. And it is equals to QL squared. QL is 614, therefore QL squared is 614 squared plus CL squared. CL is 3, therefore CL squared is 3 squared, that is 9. So in total, we have to find out that R squared equals to 614 squared plus 9. Here we open the brackets on this side of the equation and we get that R squared equals to 6 minus R squared. 6 minus R squared equals to 6 squared, that is 36, plus R squared, minus 2 times 6 times R, that is minus 12R, plus 9. So here we have R squared on both sides of this equation, so R squared get cancelled. So in this side of the equation, after I cancel R squared, we left with nothing, that is to say 0. And on the other side of the equation, we have 36 plus 9 is 45, minus 12R. So in total, 0 equals to 45 minus 12R. You add 12R to this equation. Finally, we get that 12R equals to 45. And divide this equation by 3. And finally, we get that 12R over 3 is 4R. 4R equals to 45 over 3 is 15. So 4R equals to 15, we divide this equation by 4. And finally we get that R reduce R of the semicircle equals to 15 over 4 units in its length. The reduce R of the semicircle equals to 15 over 4 units in its length. Our task is to find out the area of this semicircle. So what is the area of the semicircle? Actually, we know that the area of any semicircle equals to the area of the circle, that is pi r squared over 2. So we just find now found out that the radius r equals to 15 over 4, so it is pi over 2 times r squared. R is 15 over 4, and therefore r squared is 15 over 4 squared. So in total, we should find out that the area of the semicircle, that is the area that we're looking for in this equation, equals to pi over 2 times 15 over 4 squared. So it is pi over 2. 15 over 4 squared equals to 15 squared, that is 225 over 4 squared, it is 16. So in total, the area of the semicircle equals to 225 pi over 2 times 16. So it is 225 pi over 2 times 16. 2 times 16 is 32. So total, I should know that of this semicircle equals to either 225 pi over 32 square units in its size, or in terms of numbers, it is equal to 22.09 square units in its size. And again, of this semicircle equals to either 225 pi over 32, or in terms of numbers, of this semicircle equals to 22.09 square units in its size. So we finished with the first question. The next step, and so the second question on this lecture. Our task in this second question is to find out the area of this green shape. In the drawing, we have the right triangle ABC. This is a right angle, it can be C. Side AB of triangle ABC equals to 6 units in its length. Side AC equals to 8 units in its length. The hypotenuse BC of triangle ABC is the missing side. So inside this right triangle we have two identical circles. They touch each other at this point. So our task is to find out the area of this green shape. So first of all we will find out the graph of the hypotenuse of triangle ABC by implementing the Pythagoras theorem in this triangle ABC. Again, according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So, in the right triangle ABC, BC squared, that is the square of the hypotenuse, equal to AB square plus AC square. Okay, again, in the right triangle ABC, according to the Pythagoras theorem, BC squared, that is the square of the hypotenuse, equals to AB squared plus AC squared. BC is the missing side, so it is BC squared equals to AB squared. AB is 6, therefore AB squared is 6 squared, that is 36. Plus AC squared. AC is 8, therefore AC squared is 8 squared, that is 64. So in total, we shall know that AC squared equals to 36 plus 64, that is 100. BC squared equals to 100. So here we take a root out of this equation and find again that BC, the graph of the hypotenuse BC is equals to the square root of 100, that is 10. The hypotenuse BC equals to 10 units in its length. This is the hypotenuse BC, that equals to 10 units in its length. What is the area of triangle ABC? What is the area of the right triangle, triangle ABC? Actually, we know that the area of any triangle equals to the base of the triangle times the height over 2. We'll choose the base SAB. The height is AC because it's right 90 degrees with the base AB. This angle equals to 90 degrees. So the height is AC over 2. So we found out that the area of this right triangle ABC is equal to the base AB times the height AC over 2. So the right triangle ABC equals to the base AB, that is 6, times the height AC, that is 8, over 2. So again, the right triangle ABC equals to the base, that is 6, times the height, that is 8 over 2. 6 times 8 is 84, and 84 over 2 is 24. So in total, we found out that the area of triangle ABC is equal to 24 square units in its size. You can calculate the area of triangle ABC in another way. Actually, the area of triangle ABC equals to the base BC times the height to the base over 2. The height to the base must create 90 degrees with the base. So the area of triangle ABC is equal to the base BC times the height H to the base BC over 2. So triangle BC equals to 24 square units in size, so 24 equals to BC. BC is 10 over 2 times H. 10 over 2 is 5, so total 24 equals to 5H. 24 equals to 5H. We will divide this equation by 5 and finally get that H equals to 24 over 5, that is 4.8 units in its length. So the height H to the base is equal to 4.8 units in its length. In the next step, we define the center of this circle. This point is point P. We find the center of this circle, this point is point Q. We find the point of tendency of tangent BC with this circle, this point is point L. We define the point of tendency of tangent BC with this circle, this point is point K. We define the point of tendency of tangent AC with this circle, this point is point Z. And finally, we define the point of tendency of tangent AB with this circle, this point is point H. In the next step, we define the center radius of one circle as x. So therefore, the radius of the other circle must be also equal to x because those circles are identical. Therefore, they must have also the same radii. So in the next step, we join points Q and K together by straight line. Point Q is the center of the circle, point K is the point of the circle itself. Therefore, QK is the radius of the circle is equal to x. The radius QK that is equal to x, the radius QK is drawn to point K, that is the point of tendency of tangent BC in this small circle. Whenever you have radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius KQ. If BC is perpendicular to KQ, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. Likewise, we join points P and N together by straight line. PL is of course the radius of the circle. This is equals to x. Point L is the point of tendency of tangent BC with this small circle. Therefore, according to rule 1, this angle equals to 90 degrees. And this angle also equals to 90 degrees. In the next step, those two circles have an external arch between them at this point. That is to say they dot each other externally at this point. Whenever you have an external arch between two circles, you can implement rule 10. So please click on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes through their touching point. So in the drawing, we have those two circles touch each other at this point, point P. The center of this circle is at point O. The center of this circle is at point N. The straight line that connects their centers together is of course the straight line OM. And according to this rule 10, the straight line OM must pass through their touching point, that is point P. Again, the straight line OM must pass through point P, that is their touching point. Or OPM is one straight line. Again, OPM is one straight line according to this rule 10. We can definitely implement rule 10 in our drawing. One could, in our drawing, those two circles have an external arch between them. At this point, we find their touching point. This point is point M. The center of this circle is at point P. The center of this circle is at point Q. The straight line that connects the centers together is of course the straight line PQ. And according to rule 10, the straight line PQ must pass through their touching point, that is point M. So PMQ is one straight line. Because of the fact that the straight line PQ must pass from point M, it means that PMQ is one straight line. Okay, again, point M is the touching point of those two circles. Okay. So in the next step we will do a construction, that is to say, from point M, that is the touching point of those two circles, we will do perpendicular on BC. Again, from point M we will do perpendicular on BC. Actually, this angle equals to 90 degrees. This angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point M, from point M and MK. This point is point T. What is what is the definition of this line segment TM? Actually, line segment TM is a common tangent of those two circles. Tangent TM is tangent to this circle at point M. Tangent TM is also tangent to this circle at point M. So TM is a common tangent that belongs to both circles. So QM is of course the radius of this circle, equals to x. Why QM is the radius? Because it starts from the center of the circle and ends at point M, that is the point of the circle itself. So QM is the radius of the circle, equals to x. Likewise, PM is also the radius of the circle, for the same reason. It is equals to x. The radius QM that is equals to x, the radius QM is drawn to point M, that is the point of tendency of tangent TM with this circle. And now radius that is drawn to the point of tendency, then tangent TM will be perpendicular to the radius MQ. If TM is perpendicular to MQ, it means that this angle equals to 90 degrees according to rule 1. Likewise, in this circle, we have the radius PM that is equals to x. The radius PM is drawn to point M, that is the point of tendency of tangent TM in this circle. And whenever your radius is drawn to the point of tendency, then tangent TM will be perpendicular to the radius MP. If TM is perpendicular to MP, it means that this angle equals to 90 degrees according to rule 1. So this polynomial PMTL, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees. 270 degrees plus the size of this fourth missing angle, so that must be equal to 360 degrees according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in size. Therefore, quadrangle PMTL is a rectangle because it has 4 right angles. Likewise, in this small quadrangle MQKT, we have 1, 2, 3 rectangles, and this fourth missing angle must be equal to 90 degrees inside. Quadrangle MQKT is 4 rectangles, and therefore quadrangle MQKT is a rectangle. We know that the opposite sides of a rectangle are equal to each other. So in rectangle MQKT, side MQ is equal to the opposite side KT, but MQ is x, therefore KT must be also equal to x units in its length. Likewise, according to the sum rule, in the sum of rectangle MQKT, side QK equals to the opposite side MT, but QK is x, therefore the opposite side MT must be also equal to x unit in its length. So we have, if we focus on the big quadrangle PQKT, we have 1, 2, 3, 4 rectangles, and therefore quadrilateral PQKL is a rectangle. Now, quadrilateral, the big quadrilateral PQLK is a rectangle. According to rule 10, PMQ is one straight line, and therefore PMQ, that is PQ, in total must be equal to x plus x, that is 2x. So PQ equals to 2x units in itself according to rule 10. PQ equals to 2x. Okay, in after PQLT, side PQ is equal to the opposite side LK. But PQ is 2x, therefore LK must be also equal to 2x units in its length. So LK must be also equal to 2x units in its length. So in the next step, I'll copy this big rectangle PQKL with those two small rectangles in a new drawing, and we'll actually draw another construction in the new drawing. So I'll copy those three rectangles in the new page. With again PQ equals to 2x units in its length. Likewise, LK also equals to 2x units in its length. And PQLK is a rectangle. On the other, PQLK is a rectangle. So actually, this is rectangle PQLK that according from the original drawing. PQ equals to 2x, LK also equals to 2x. QK of course is the radius of the circle, that is x. LK is the radius of the circle, that is X. So in the next step, we join points A and P together by a straight line. But before that, we already found out that the height to the base BC of triangle ABC equals to H. So I will draw the height to the base BC from the vertex A of triangle ABC. And we already found out that the height H of this, the height to the base BC of this triangle ABC equals to 4.8 units in its length. So we'll go from point A, we'll go perpendicular on BC, and this will be the height to the base BC. It equals to H, and H equals to 4.8. So actually, this angle equals to 90 degrees. And this angle also equals to 90 degrees. According to our construction, we define the touching point of the perpendicular from point A and BC. This point is point S. As I already mentioned before, AES is the height to the base BC, because it's 90 degrees to the base BC. So AES equals to H. That is the height to the base BC. AES equals to H, and we only found out that H, the height to the base BC, ABC equals to 4.8 units in its length. In the next step, we'll do a construction. That is to say, we'll join points A and P together by a straight line, and then we'll join points A and Q together by a straight line. By doing this construction, we will have triangle APQ. We define the intersection point between AS and PQ. This point is point F. Repeat again, the base PQ of the small triangle APQ equals to 2x units in its length. So we define the intersection point between AS and PQ. This point is point F. So those two angles are defined as corresponding angles and are located between the power lines PQ and LK. Yeah. Those two corresponding angles are located between the power lines PQ and LK. Why PQ is parallel to LK? Because of the fact that PQKL is a rectangle, and we know that the opposite sides of a rectangle are parallel to each other. So in rectangle PQKL, PQ is parallel to LK. So those two corresponding angles are located between the parallels PQ and LK, and therefore they are equal to each other in their sizes. But this angle equals to 90 degrees, and therefore this angle must be equal to 90 degrees in its size. Likewise, those two corresponding areas are located between the same lines. Therefore, they are equal to each other in their sizes. But this area equals to 90 degrees, and therefore this missing area must be equal to 90 degrees in its size. So actually, the sum of the areas on one side of a straight line is equal to 180 degrees according to all three. If you focus on the right side of the straight line AS is definitely a straight line because it is the height to the base BC. So the sum of the areas on the right side of the straight line AS at point F must be equal to 180 degrees according to all three. So this angle equals to 90 degrees, and therefore the missing angle must be equal to 90 degrees in size according to all three. Likewise, the sum of the angles on the left side of AS point F must be equal to 180 degrees. This angle equals to 90 degrees, and therefore the missing angle must be equal to 90 degrees in its size. So in quadrangle FQSK we have 1, 2, 3 angles, and therefore this fourth missing angle must be equal to 90 degrees in its size. Therefore this small quadrangle that has 4 angles, it is a rectangle. But we know that the opposite sides of a rectangle are equal to each other. So in the small rectangle FQKS, side QK is equal to the opposite side FS, but QK is X, therefore the opposite side FS must be also equal to X units in its length. So, conclusion found out that Fs equals to X units in its length. Quadrangle PFSL is also a rectangle, but it is not relevant here, because we only found out that Fs equals to X. What is the length of this line segment AF? AF, it is actually the height to the base PQ of the small triangle PQ. Again, AF is the height to the base PQ of triangle PAQ. So what is the length of the height AF? AF from the drawing it is very easy to do that AF equals to in total to AS minus FS. Again, AS minus FS equals to AF. So I know AF equals to AS minus FS. So AF in total equals to AS. AS is the height to the base BC, that is H, and H is 4.8. Minus Fs. We just found out that Fs equals to X. Fs equals to X. So in total, we actually found out that the height AF to the base PQ of triangle, the small triangle PQ equals to 4.8 minus X units in its length. What is the area of this small triangle APQ? Okay, again, what is the area of this small triangle APQ? The area of any triangle equals to the base PQ times the height AF. We already found out that PQ equals to 2x units in its length. The height AF is 4.8 minus X, and therefore total the area of triangle APQ must be equal to the base, that is 2x times the height, that is 4.8 minus X divided by 2. So at the end we found out that the area of this small triangle APQ total is equals to the base of the triangle, that is PQ, times the height to the base, that is AF over 2. And again, if we found out that the area of this small triangle APQ, in total it is equals to the base PQ times the height AF over 2. PQ equals to 2x. PQ equals to 2x. We just write down further that the height AF equals to 4.8 minus x. 4.8 minus x. And we have to divide it by 2. So in total, we actually found out that the area of this small triangle APQ is equal to 2x times 4.8 minus x over 2. We have 2 in the numerator, 2 in the denominator, so 2 get cancelled. So cancel 2, we have to only with x times 4.8 minus x. Here we'll open the brackets, this expression, and get that x times 4.8 is 4.8x. X minus x is minus x squared. So in total, we should find out that the area of the small triangle APQ is equal to 4.8x minus x squared. Squared is inside. And again, the area of this small triangle APQ in total it is equal to 4.8x minus x squared. Squared is in size. So in the next step, we'll join points P and B together by a straight line. Likewise, we'll define the point of tendency of tangent AB with this circle. This point is point Y. And we join points P and Y together by a straight line. PY is of course the radius of the circle is equals to x. Point Y is the point of tendency of tangent AB with this circle, and therefore according to rule 1, this angle equals to 90 degrees. This angle also equals to 90 degrees. In the next step, we join points Q and C together by a straight line. We define the point of tendency of tangent AC with this circle. This point is point G. And we join points Q and G together by a straight line. QG is of course the radius of the circle that equals to x. Again, point G is the point of tendency of tangent AC with the circle, and according to 1, this angle equals to 90 degrees. And this angle also equals to 90 degrees. We already found out that the area of this big right triangle ABC equals to 24 square units in size. But the right triangle ABC consists of six shapes. This is the first shape, that is triangle APB. This is the second shape, that is triangle AQP. This is the third shape, that is triangle BPL. This is the fourth shape, that is triangle QKC. This is the fifth shape, that is triangle PQKL. And this is the sixth shape, that is triangle APQ. And it is very clear that the triangle ABC must be equal to the sum of the areas of the six shapes that it consists of. 23 must be equal to those two the 6 steps that I mentioned. So we will find out the area of each shape separately, and then we let areas of the 6 shapes together, and this will be the area of triangle ABC, that is 24. By creating this equation, we will create a biggest expression that the only variable that will be missing in the equation is x. We will express all the 6 shapes, the areas of this, all those 6 shapes in terms of x. And the sum of the areas of the 6 shapes must be equal to the area ABC, that is 24. So 24 equals to some expression with x. That is the only variable that is missing. So by solving one equation with one variable, we get the value of x. That is the radius of the circle. And there are this green shape will be equal to the big right triangle ABC minus those two small circles. And the area of those small circles will be equal to the area of one circle times 2, because they are identical, therefore they have the same areas. The area of one circle must be equal to pi x squared. So 2 times pi x squared equals to the area of those two circles. So the area of this triangle ABC, that is 24, minus the area of those two circles, that equals to 2 pi x squared. This is the area of the green shape, that is the area that we are looking for in this expression. So it is very simple, but we have to do a lot of work to arrive to the results. Okay, so first of all, I'll write down the equation that the area of this big triangle ABC must be equal to the sum of the areas of the 6 shapes that it consists of. So the area of triangle ABC equals to the area of the first shape that it consists of, that is triangle APB, this is the triangle APB, plus the area of the second shape that it consists of, that is this triangle AQC, plus the area of the third shape that is the triangle ABC consists of, this is actually the right triangle PEL, plus the area of the fourth shape that triangle ABC consists of, this is actually the area of this right triangle QKC, plus the area of this fifth shape that triangle ABC consists of, this is actually rectangle PQKL. Plus the area of this sixth shape that triangle ABC consists of, that is triangle APQ. So this normal question says that the area of triangle ABC must be equal to the sum of the areas of the 6 shapes that it consists of. The sum of the 6 shapes that it consists of. Consists of triangle APB plus the area of triangle AQC plus the area of triangle PBL plus the area of triangle KQC plus the area of triangle PQKL plus the area of triangle APQ. So we found out that the area of triangle ABC equals to 24 square instances, so we solve the area of triangle ABC by 24. So 24 equals to the area of triangle APB. What is the area of this triangle APB? On the drawing, it is very easy to say that the area of triangle APB equals to the base AB times the height TP over 2. Again, the area of this triangle APB equals to the base AB times the height TP over 2. AB AP is 6 according to the given equation. Again, the base AB equals to 6 units now. The height YP is x. So the base, that is 6 times the height x over 2. It is actually 6x over 2. So in total, the area of this triangle APB equals to 6x over 2. 6x over 2. So the area of triangle APB equals to 6x over 2 plus the area of triangle AQC. What is the area of this triangle? Again, AQC is equal to the base AC, that is 8, times the height of the base QG, that is x over 2. So it is 8x over 2. Okay. The second shape, there of the second shape, that is again AQC in total equals to 8x over 2 plus this right triangle PBL. What is the of this right triangle PBL? It is equal to the base BL times the height LP, that is x over 2. So there of the fourth shape that triangle ABC consists of, it's actually the area of triangle PBL, that equals to the base BL times x over 2. Plus there of the fifth shape, actually it is the plus there of the fourth shape, that is there of this triangle QKC. What is there of this triangle QKC? It is equal to the base KC times the height to the base QK, that is x over 2. So they have the fourth shape that triangle ABC consists of. This is actually the area of the triangle QKC, that equals to the base KC times the height x over 2. It is KC over 2. As they have the fifth shape, they have this rectangle PLQC. The length of the rectangle PQKC. The rectangle PQKL. The rectangle PQKL. The area of rectangle equals to the length times the width. The length PQ is 2x, the width PL is x. So the length times the width is 2x times x. So now the fifth shape the triangle ABC consists of is the rectangle PQ here, that equals to 2x plus times x, plus the of the sixth shape that triangle ABC consists of. So we found out that the area of this triangle APQ in total it is equals to 4.8x minus x squared. Now the sixth shape that triangle consists of is that line AP equals to 4.8x minus x squared. So 24 equals to 6x over 2 is 3x, plus 8x over 2 is 4x. Here BL times x over 2 plus QL plus KL times x over 2. Here we take x over 2 as a common factor from those two expressions. So what is left from this expression? This expression after we took from it x over 2 is a common factor. What is left is actually BL plus what is left from this expression after we took from it x over 2 is a common factor. What is left is actually KC. Plus 2x times x is 2x squared. Plus 4.8x minus x squared. So if you found out that 24 equals to 3x plus 4x is 7x plus x over 2 plus BL plus KC. What is the value of BL plus KC? What is the value of BL plus KC? Actually, it is very clear from the drawing that if we remove from BC this line segment LK, what is left from BC after we remove line segment LK? What is left is BL plus KC. Again, what is left from BC if we remove from BC line segment LK? What is left is actually BL plus KC. So BL plus KC equals to BC, that is 10, minus KL, that is 2x, which is 10 minus 2x. Yeah, KL equals to 2x. KL equals to 2x. Okay, so in total, BL plus KC equals to 10 minus 2x units since so 24 equals to 7x plus, I will open the brackets of this expression, 10 over 2 is 5, so x over 2 times 10 is 5x. And we have x over 2 times minus 2x. We have 2 the denominator, 2 the denominators, so 2 will get cancelled, and we left only with minus x. So it is x times minus x is minus x squared plus 2x squared plus 4.8x minus x squared. So 24 equals to 7x plus 5x is 12x. So here we have minus x squared is minus 2x squared, minus 2x squared plus 2x squared is 0. So those two expressions will get cancelled, and we're left only with 4.8x. So we found out that 24 equals to 12x plus 4.8x. So 24 equals to 12x plus 4.8. What is the value of 12x plus 4.8? X is 16.8x. So in total, I have found out that 24 equals to 16.8x. Here we divide this equation by 16.8. We get that the radius x on the circle, on the two circles, is equal to 24 over 16.8 units in its length. The radius x of those two circles is equal to 24 over 16.8 units in its length. Our task is to find out the area of this dimension. So I explained to you a couple of minutes ago the area of this dimension. Must be equal to the area of the big right triangle ABC. We know that is 24 square units. Minus the area of those two circles. So I'll explain you. The area of those two circles in total equals to the area of one circle times 2 because they are identical. The area of one circle is pi x squared. For the area of the two circles equals to 2 pi x squared. So in total, again here equals to the area of the ABC, that is 24 square units in size, minus 2 times pi times x squared. X is 24 over 16.8, therefore x squared is 24 over 16.8 24 over 16.8 squared. What is the value of this expression? 2 pi times 24 over 6.8. So in total, the value of this expression is equal to 12.823. So in total, the differential equals to 24 minus 12.823. That equals to 11.177 square units in size. That is the answer to the question. And again, the area that we are working for this question. This is the area of the screen shape. In total, it equals to 11.177 square units in size. So we finish with the second question. In the next step, as well as the lecture, we'll start with the first question, of course. in the first question, our task is to find out the area of this semicircle that is inside this big quarter circle A or B. Repeat again. The first question, our task is to find out the area of this semicircle that is inside quarter circle A or B. So, in the drawing, we have quarter circle A or B. This is a right angle. OS equals to 4 units in its length. Inside this quarter circle, we have this semicircle. And we also know that arc AQ equals to arc QB in its length. Again, our task is to find out the area of this semicircle that is inside quarter circle A or B. So first of all, we define the center of this semicircle. This point is point C. We define the radius of this semicircle as R. We define the touching point between the semicircle and the quarter circle. This point is point P. So CP is of course the radius of the semicircle is equals to R. Likewise, CQ is also the radius of the semicircle that is equals to R. So, in the next step, we join point C and S together by side line. Point S is the point of tendency of tangent OB with this semicircle. So we join point C and S together by side line. Point C is the center of the semicircle, point S is the point of the semicircle itself, therefore CS is the radius of the semicircle that is equals to R according to our definition. The radius CS that is equals to R, the radius CS is 1 to point S, that is the point of tendency of tangent OB with this semicircle. And now that is 1 to the point of tendency, then tangent OB will be perpendicular to the radius SC. If OB is perpendicular to SC, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So, in the next step, we did a construction, that is to say, from point Q, we do perpendicular on OB. Again, from point Q, we do perpendicular on OB. So this angle equals to 90 degrees, this angle also equals to 90 degrees according to our construction. So actually we have here the sum of those two angles is 180 degrees. Those two angles are defined as one-sided interangles, and whenever the sum of two one-sided interangles is equal to 180 degrees, they must be located between parallel lines. That is to say, PO is parallel to CS according to rule 22. So I'll get quickly on rule 22. According to rule 22, if the sum of two one-sided interangles is equal to 180 degrees, then they are located between parallel lines. Those two angles alpha and beta are defined as one-sided interangles, and they are located. So if alpha plus beta, if the sum of those two one-sided interangles is equal to 180 degrees, that is to say, if alpha plus beta equals to 180 degrees, then they are located between parallel lines. That is to say, line A is parallel to line B. So, as mentioned before, we can implement rule 22 in our drawing, because the sum of those two one-sided interangles is equal to 180 degrees, and therefore they must be located between parallel lines. That is to say, PO equals to CS. PO is parallel to CS according to rule 22. Here, PO is parallel to CS according to rule 22. Likewise, the sum of those two one-sided interangles is equal to 180 degrees. Therefore, they are located between parallel lines. That is to say, CS is parallel to LM. CS is parallel to QM. CS is parallel to QM. Likewise, the sum of those two one-sided interangles is equal to 180 degrees. And therefore, we are located they are located between the parallel lines. That is to say, PO is parallel to QM. PO is parallel to QM. So in total, we should find out that those three lines, PO, CS, and QM, they are parallel to each other. PO is parallel to CS, is parallel to QM. So whenever you have whenever you have three or more parallel lines, and you have also line segments that connects between the parallel lines, in this case, QP connects the three parallel lines, and also MO also connects the three parallel lines together, then you can implement this theorem. Okay. Again, we have three parallel lines. QM is parallel to CS and parallel to PO. QP connects the three parallel lines, and also connects the three parallel lines together. And according to Thales theorem, we have a relationship, a special relationship between those two lines that connects the three parallel lines. That is to say, between line QP and line MO. They are the lines that connect the three parallel lines together. The relationship between those two lines that connects the three parallel lines together is as follows. PC over CQ equals to OS over SM. PC over CQ equals to OS over SM. So I put quickly on Thales theorem. BO is parallel to CS, is parallel to QT. PQ connects the three parallel lines. OT also connects the three parallel lines. So we have a special relationship between those two line segments that connects the three parallel lines together. The relationship is as follows. PC over CQ equals to OS over ST. Again, PC over CQ equals to OS over ST. So in our model, we have PO is parallel to CS, is parallel to QM. PQ connects the three parallel lines together. OM also connects the three parallel lines together. So we have a special relationship between those two line segments that connects the three parallel lines together. The relationship is as follows: PC over CQ equals to OS over SM. And according to this theorem, PC over CQ equals to OS over SM. PC is R, CQ is R, OS is 3. Again, PC is R, CQ is R, OS is 3, over SM. R over R is 1, so 1 equals to 3 over SM. Here we multiply this equation by SM, and find out that SM equals to 3 units in SM. This is, let me see, 9 SM, this equals to 3 units in SM. In the next step, we join points Q and all together by a straight line. We join points Q and U, okay, the entire QOM. This is, we know that point O is the center of the quarter circle, and therefore AOQ is the center angle. Again, AOQ is the center angle because the vertex O, again, AOQ is located in the center of the circle. Therefore, angle AOQ is the center angle. Likewise, angle BOQ is also a center angle. Those two center angles, this is center angle AOQ that subtend on arc AQ. Likewise, this is center angle BOQ that subtend on arc QB. and because of the fact that those two straight triangles subtend on equal arcs, they must be equal to each other in their sizes. It is given us a question that A arc AQ equals to arc QB. So those straight triangles must be equal to each other in their sizes because they are subtend on equal arcs. AQ equals to QB. So I print quickly on rule 23. According to rule 23, set triangles that subtend on equal arcs are equal to each other and their sizes. Then normally we have a circle. This is set triangle UB that subtend on arc AB. Likewise, this is set triangle COD that subtend on arc CD. If arc AB equals to arc CD, those two set triangles must be equal to each other and their sizes. That is to say, alpha equals to beta. So I can implement rule 23 number 1. Of course, we have those two straight triangles subtend on equal arcs. That is to say, AQ equals to QB. Therefore, they must be equal to each other and their sizes. So if you define the size of this angle as theta, then the size of this angle must be also equal to theta because they are equal to each other according to rule 23. Theta plus theta is 90 degrees because angle UB is right angle. Theta plus theta is 2 theta, that is 90 degrees, and therefore theta equals to 45 degrees inside. This is angle theta, that equals to 45 degrees inside. So in triangle, the right triangle QOM sinus 45 degrees equals to QOM over MO. In the right triangle QOM, sinus 45 degrees equals to QM over OM. Sinus 45 degrees is 1 equals to QM over OM. So it's QM over OM. OM in total equals to 3 plus 3, that is 6. So in total, we have MQ over MO. This is OM, that equals to 6, so that OM by 6. So 1 equals to QM over 6, and we multiply this equation by 6 and found out that QM equals to 6 units in its length. QM equals to 6 units in its length. In the next step, we did another construction, that is to say, from point C, that is the center of the circle, we go perpendicular on QM. We go from point C, that is the center of this semicircle, we go perpendicular on QM. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C in QM, this point L. When doing this construction, we're going to do quadrangle CLMS. In quadrangle CLMS, we have 1, 2, 3 right angles. The sum of right angles is 270 degrees. 270 degrees plus the size of this four-piece angle, in total must be equal to 360 degrees according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, this four-piece angle must be equal to 90 degrees in size. So in quadrangle CLMS, we have 4 right angles, and therefore it is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle CLMS, side CL must be equal to the opposite side SM, but SM is 3, therefore the opposite side CL must be also equal to 1 in its length. Likewise, according to the sum rule, in the same rectangle CLMS, side CS must be equal to the opposite side LM, but CS is R, this is the radius of the circle, therefore LM must be also equal to 1 unit in its length. What is the length of line segment QL? QL equals to QM minus LM. QL equals to QM minus LM. So QL equals to QM, that is 6, minus LM, that is also in total. QL equals to 6 minus 1 unit in its length. In the next step, with this right triangle QCL in the page, we implemented the quadrilateral in this right triangle QCL. Actually, this is the right triangle QCL, that the point from the original drawing. This right triangle QCL, only to the quadrilateral theorem QC squared, that is the square of the hypotenuse, equals to QL squared plus CL squared. QC is R, therefore QC squared is R squared, and it equals to QL squared. QL is 6 minus R, therefore QL squared is 6 minus R squared. plus CL square. CL is 3, therefore CL square is 3 square, that is 9. So in total, R square equals to 6 times R square plus 9. So R square equals to 6 times R square. 6 times R square equals to 6 square, that is 36, plus R square minus 2 times 6 times R, that is minus 12R plus 9. We have R square on both sides of this equation, so R square will get cancelled. So in this side of the equation we left with nothing, that is to say 0, while in the other side of the equation we have 36 plus 9, that is 45 minus 12R. So 0 equals to 45 minus 2R. Here we add 45 to this equation, 500 12R equals to 45. Here we divide this equation by 3, 500 12R over 3 is 4R, equals to 45 over 3 is 15. So in total, 4R equals to 15. Here we divide the equation by 4 and find 400R, the radius of this semicircle, is equal to 15 over 4 units in its length. Our task is to find out the area of this semicircle. Actually, we know that the area of any semicircle equals to the area of the circle, that is pi r square over 2. So the area of another semicircle must be equal to pi r square over 2. R is 15 over 4, so it is pi over 2 times r square. R is 15 over 4, therefore r square is 15 over 4 squared. So in total, the area of the semicircle must be equal to pi over 2 times 15 over 4 squared. 15 over 4 squared equals to 15 squared, that is 225, over 4 squared, that is 16. So in total, the semicircle equals to 225 pi over 2 times 16. 2 times 16 is 32. So in total, the area of this semicircle is equal to either 225 pi over 32 square units in size, or in terms of numbers, the area of this semicircle equals to 22.09 square units in size. So we finish with the first question. In the next step, we'll repeat on the solution of the second question. In the second question, our task is to find out the area of this given shape. So in the drawing, we have the triangle ABC. Inside this triangle ABC, we have those two identical circles. AB equals to 6, AC equals to 8. Again, our task is to find out the area of this shaded area. This is angle BC, this is right angle. So in the first step, we implemented the Pythagoras theorem on this triangle ABC in order to find out the hypotenuse BC. Only to the Pythagoras theorem, BC square equals to AB square plus AC square. Now triangle ABC, according to the Pythagoras theorem, BC square equals to AB square plus AC square. The hypotenuse BC is the missing side, so it is BC square equals to AB square. AB is 6, therefore AB square is 6 squared, that is 36, plus AC square. AC is 8, therefore AC square is 8 squared, that is 64. So in total, BC square equals to 36 plus 64. 36 plus 64 is 100. So BC square equals to 100. Here we took order of this value, and we found out that BC equals to the square root of 100, it is 10. The length of the hypotenuse BC is equal to 10 units. What is the area of the triangle ABC? The right triangle ABC, the area of one triangle equals to the base of the triangle times the height over 2. The base is AB, the height is AC over 2. So the area of triangle ABC equals to the base AB times the height AC over 2. AB is 6, AC is 8. 26 times 8 over 2. 6 times 8 is 48 over 2 is 24. 48 over 2 is 24. So do not show that this right triangle ABC equals to 24 square meters in size. We can find out the area of triangle ABC in the different method. We choose the base as BC. If we choose the base of triangle ABC as BC, then it will be equal to the base BC times the height to the base, that is h over 2. Okay. The area of triangle ABC equals to the base BC times the height to the base BC over 2. The height must get 90 degrees with the base. So, the area of triangle ABC equals to the base BC times the height h over 2. The area of triangle ABC equals to 24 square meters in size, so 24 equals to BC times h over 2. BC is 10, so the BC is 10. If we found out that 24 equals to 10 over 2 is 5. So put the 24 equals to 5h. Here we divided this equation by 5 and finally found out that the height of to the base BC of this big triangle ABC is equal to 4.8 units in its length. The height h to the base BC equals to 4.8 units in its length. In the next step, we define the center of this circle, this point is point P. We define the center of this circle, this point is point Q. We define the point of tendency of tangent BC with this circle, this point is point L. We define the point of tendency of tangent BC with this circle, this point is point K. We define the point of tendency of tangent AB with this circle, this point is point H. We define the point of tendency of tangent AC with this circle, this point is point Z. We define the radius of the one circle is X. For the fact that those two circles are identical, the radius of the other circle must be also equal to x units in its length. We join points P and N together by a straight line. Point P is the center of the circle, point L is the point of the circle itself, therefore PL is the radius of the circle, is equals to x. According to our definition, the radius PL is equals to x, the radius PL is drawn to point L, that is the point of tendency of tangent BC. With this circle, radius which is drawn to the point of tendency, then tangent BC will be perpendicular to the radius LP. If BC is perpendicular to LP, it means that this angle equals to 90 degrees. This angle also equals to 90 degrees, according to rule 1. Likewise, we join points Q and K together by straight line. QK is the radius of the circle that is equals to x. Point K is the point of tendency of tangent BC with this circle. According to 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So, here, we define the touching point between those two circles. This point is point M. So, here we can implement rule 10. Why? Because of the fact that those two circles have an external arch between them at point M. That is to say, they touch each other externally at point M. Whenever you have an external arch between two circles, you can implement rule 10. Quick rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects the circles together passes for their touching point. So in the drawing, we have those two circles that touch each other externally at point P. Point O is the center of this circle, point M is the center of this circle, and the straight line that connects the circles together is of course the straight line OM. According to this rule 10, the straight line OM must pass for point P, that is their touching point. Again, the straight line OM must pass for their touching point, that is point P. Or in other words, OPM is one straight line. Again, OPM is one straight line according to this rule 10. So we can implement rule 10 in our drawing. Point P is the center of this circle. First of all, someone mentioned before, those two circles have an external between them at point M, and therefore we can implement rule 10. Point P is the center of this circle, point Q is the center of this circle. the third line that connects the circles together is the third line PQ. And according to rule 10, the third line PQ must pass through point M, that is the attaching point. Or PMQ is one third line. Again, PMQ is one third line. If PMQ is one third line, it means that PQ in total must be equal to PM plus MQ. Okay. So, in the next step we did the construction, that is to say from point M we draw perpendicular on BC. Again, from point M we draw perpendicular on BC. So this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point M and BC. This point is point T. What is the definition of line 70M? Line 70M is a common tangent that belongs to both triangles, right? Tangent TM is tangent to this circle, tangent TM is also tangent to this circle. Okay, so the radius QM is equal to X is drawn to point M, that is the point of tendency, or tangent TM if this circle. The radius is drawn to the point of tendency, then tangent TM will be perpendicular to the radius MQ. If TM is perpendicular to MQ, it means that this angle equals to 90 degrees according to 1. Likewise, the radius VM that is equals to X. Since PM is drawn to point M, that is the point of tendency of tangent TM in this circle, and therefore according to 1, this angle equals to 90 degrees. So we have quadrangle MQKT. This third quadrangle MQKT, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. 270 degrees plus the size of this fourth piece again, in total must be equal to 360 degrees, according to the rule that says that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore, this fourth piece again must be equal to 90 degrees inside. So inside quadrangle TMQK we have 4 right angles, therefore the small quadrangle TMQK is a rectangle. Likewise, in this small quadrangle PMTL, we have 1, 2, 3 right angles, and therefore the fourth missing angle must be equal to 90 degrees inside. Therefore, quadrangle PMTL is a rectangle. So those two small quadrangles are both rectangles. What about the big quadrangle PQKL? The big quadrangle PQKL is 1, 2, 3, 4 right angles, and therefore the big quadrangle PQKL is a rectangle. Quadrangle PKQL is a rectangle. In the next step, I copied the big rectangle PQKL in a new page, and then we did the construction in the new page. This is rectangle PQKL that is coming from the original drawing. PL is the radius. The second equals to X, QK equals to X. But before that, according to PM equals to X, which is the radius of the circle, QM also equals to X, that is the radius of the circle. According to rule 10, PQ in total equals to PM plus MQ. So PQ equals to X plus X, that is 2X. Again, PQ equals to 2X. And because of the fact that PQKL is a rectangle, the opposite sides of rectangle are equal to each other. So, rectangle PQKL, side PQ must be equal to the opposite side LK. Therefore, LK must be also equal, that PQ equals to 2X, therefore LK must be also equal to 2X when it's incident. LK equals to 2X. So, PQ equals to 2X, LK also equals to 2X. Okay, again, LK equals to 2X, PQ also equals to 2X units in itself, according to what we already found out. We already found out that the height to the base of the big rectangle ABC is equal to H, and H equals to 4.8. So from point A, we do perpendicular on BC. The perpendicular is definitely the height to the base, because the height must create 90 degrees with the base. So AS is the height to the base BC of the big triangle ABC. AS equals to H and H equals to 4.8. In total, we found out that AS, that is the height to the base of the triangle ABC, the height to the base BC of the big triangle ABC is equal to H and H equals to 4.8 units in its length. Again, AS equals to 4.8 units in its length. So PQKL is a rectangle. We know that the opposite sides of a rectangle are parallel to each other. So in the big rectangle PQKL, side PQ is parallel to the opposite side LK. Those two angles are located between two parallels, that is to say PQ and KL, and therefore they are equal to each other on their sides. But this angle equals to 90 degrees, therefore this missing angle must be equal to 90 degrees in size. Likewise, those two angles are both located between the same parallels, and according to know that corresponding angles between parallels are equal to each other, they must be equal to each other in their sizes. But this is a right angle, therefore this angle must be also a right angle. According to rule 3, the sum of the angles on one side of a straight line is equal to 180 degrees. AS is the height to the base, BC, therefore it is definitely a straight line. So if you focus on the right side of the straight line AS point F, the sum of the angles must be equal to 180 degrees. According to rule 3. So which angles we have in the right side of the straight line AS point F? We have 90 degrees plus the missing angle must be equal to 180 degrees, and therefore this missing angle must be equal to 90 degrees in its size. Likewise, the sum of the angles on the left side of the straight line AS point F must be equal to 180 degrees according to rule 3. So which angles we have the left side of the straight line AS point F? We have, this is the right angle plus the missing angle must be equal to 180 degrees in its size, therefore this missing angle must be equal to 90 degrees in its size according to rule 3. So in quadrangle PQSK we have 1, 2, 3 rectangles, and therefore the fourth missing angle must be equal to 90 degrees in its size. So quadrangle PQKS is a rectangle because it has 4 rectangles. But we also know that the opposite sides of a rectangle are equal to each other. So in the rectangle FQKS, side KQ, side QK equals to the opposite side FS. But QK equals to X, and therefore the opposite side FS must be equal to X units in its length. AS equals to H equals to 4.8. H equals to in total to 4.8 units in its length. What is the length of AF? From the drawing it is very easy to see that AF in total equals to AS minus FS. Again, AF equals to AS minus FS. So AF in total equals to AS, that is 4.8, minus FS, that is X. Again, AF in total equals to AS, that is 4.8, minus FS, that is X. So in total, we should found out that AF equals to 4.8 minus X units in its length. What is the of this? Actually join points A and P together by straight line, and join points A and Q together by straight line. In this case we created triangle APQ. The height to the base PQ for triangle APQ is AF, that is 4.8 minus X. The base PQ equals to 2X. Only to what we found out, the base PQ, the small triangle AP equals to 2X. PQ equals to 2X. The height to the base AF equals to 4.8 minus X. Thereafter, APQ equals to the base PQ times the height AF over 2. And again, thereafter this triangle APQ equals to the base PQ times the height to the base AF over 2. PQ is 2X, AF is 4.8 minus X. Repeat again, PQ is 2X, AF is 4.8 minus X, divided by 2. We have 2 in the denominator, so 2 will get cancelled, and then left only X times 4.8 minus X. We open the brackets here, and found out already that X times 4.8 is 4.8X. X times 1x equals to 1x squared. So in total, we found out that the area of this small triangle APQ is equal to 4.8 minus x squared, so it's in its size. In the next step, we join points P and B together by straight line. Likewise, we define the point of tendency of the AB with this area. This point is point Y. Join points P and Y together by side line. Py is of course the radius of this area that is equal to x. And according to 1, this angle equals to 90 degrees, this angle also equals to 90 degrees. Likewise, we join points Q and G together by side line. QG is of course the radius of the circle that is equals to x. Point G is the point of tendency of tangent AC with this small circle. Therefore, according to 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So, we only found out that thereafter, the right triangle ABC is equals to 24 squares in size. The right triangle ABC consists of 6 shapes. And therefore, the right triangle ABC must be equal to the sum of the rest of the 6 shapes that it consists of. The first shape is this triangle APB, plus the second shape is this triangle AQC, plus the third shape, this is the right triangle PBL, the fourth shape is the right triangle QKC, this is the fifth shape of triangle ABC, consists of the right triangle PQKL, plus they have the sixth shape, that is triangle APQ, so the sum of those two six shapes must be equal to the right ABC, that is equals to 24 square centimeters. And again, the of the other ABC must be equal to the sum of the rest of the 6 shapes that it consists of. 1, 2, 3, 4, 5, 6. The first shape is triangle APB, plus they have the second shape that is triangle AQC, plus they have the third shape that is triangle ABC consists of, that is actually the triangle PBL, plus they have the fourth shape that triangle ABC consists of, that is actually the triangle QKC, plus they have the fifth shape that triangle ABC consists of, that is actually triangle PQKL, plus they have the sixth shape that is triangle ABC consists of, that is actually triangle APQ. What is the triangle APB? What is the triangle APB? The triangle APB must be equal to the base AB times the height to the base YP over 2. AB is 6, YP is x, divided by 2. So it is 6x over 2. Now triangle APB equals to 6x over 2. Plus they have this triangle AQC. What is this triangle AQC? It is equals to the base AC times the height to the base PQ over 2. AB is 8, EQ is x over 2. So it is 8x over 2. AQ, the second shape, we have the second shape, triangle AQC in total equals to 8x over 2. So the second shape is 8x over 2. Plus they have the third shape that triangle ABC consists of, is actually they have this right triangle PBL. They have this right triangle PBL equals to the base BL times the height LP over 2. LP is x, so in total it is equals to the base BL times x over 2. So they have the fourth shape that triangle ABC consists of equals to BL, it is the third shape, it is BL times x over 2. Plus they have this fourth shape that triangle ABC consists of, this is actually the right triangle QKC, that is equals to the base KC times the height KQ, that is x over 2. So it is KC times x over 2. They have the fourth shape that triangle ABC consists of, is KC times x over 2. Plus they have this fifth shape that triangle ABC consists of, actually they have this rectangle, then PQKL. But again, we already found out that PQ, polynomial PQKL is a rectangle. Okay. Polynomial PQKL is a rectangle. So the rectangle equals to the length PQ times the height, the length PQ times the width PL over 2. And we found out that the length PQ equals to 2x and the width is x. So it is 2x times x. So now the fifth shape is the rectangle PQPL, that is 2x times x. Plus they have the sixth shape that triangle ABC consists of, actually they have the small triangle APQ. We only found out that the small triangle AP2. In total, it is equal to 4.8 x minus x squared, square units in its size. So here we already found out that the triangle ABC equals to 24 square units in its size. 6x over 2 is 3x, 8x over 2 is 4x. Here we have BL times x over 2 plus KC times x over 2. We took x over 2 as a common factor from those two expressions. So what is left from this expression after we took from it x over 2 as a common factor? What is left is actually BL. What is left from this expression after we took from it x over 2 as a common factor? What is left is actually KC. And we have 2x times x is 2x squared. We have here 4.8x minus x squared. So 24 equals to 3x plus 4x is 7x. And we have x over 2. What is the value of BL plus KC? We must express all the of those three shapes in terms of x. And then we'll have one variable that in one equation. We are able to solve one variable in one equation. So we have to express BL plus KC in terms of x. This is 97 BL, this is 97 KC. What is the value of BL plus KC? From the drawing, it is very easy to see that if you remove from BC 97 LK, what is left? What is left is BL plus KC. Again, if you remove from side BC 97 LK, what is left is actually BL plus KC. So in total, BL plus KC must be equal to BC minus LK. BC is 10, LK is 2x. LK is 2x. LK is 2x. So in total, BL plus KC equals to BC that is 10, BC that is 10 minus LK, it is 2x. Total BL plus KC equals to 10 minus 2x units in its name. So BL plus KC equals to 10 minus 2x units in its name. And we have 2x squared plus 4.8x minus x squared. So 24 equals to 7x squared. 24 equals to 7x. We open the brackets of this expression. 10 over 2 is 5, so in total this expression equals to 5x. Here we have x over 2 times minus 2x. Minus 2 over 2 is minus 1, so it is minus x times x, that is minus x squared, plus 2x squared plus 4.8x minus x squared. So in total, 24 equals to 7x plus 5x is 12x. And we have minus x squared. Minus x squared is minus 2x squared. Minus 2x squared plus 2x squared is 0. So in total, those four expressions will get cancelled. And we have only 4.8x. So in total, 24 equals to 12x plus 4.8x. 12x plus 4.8x equals to 16.8x. So in total, 24 equals to 16.8x. And again, if we found out that 24 equals to 16.8x. Here we divided the equation by 16.8 and we found out that x, that is the radius of the circle, equals to 24 over 16.8 units in its length. So division 4, the area of this green shape equals to the area of the big right triangle ABC minus the area of those two small circles. So the area of the green shape equals to the area of the triangle ABC minus the area of those two circles. The area of those two circles in total equals to the area of one circle times 2 because they are identical. The area of one circle is pi x squared, therefore the area of those two circles is equals to 2 pi x squared. 2 pi x squared. So now the sum of the areas of the two circles equals to minus 2 pi x squared. The area of the ABC is 24. Here minus 2 pi x squared. It is 2 pi, x is 24 over 16.8, and therefore x squared is 24 over 16.8 squared. So in total, the area of the green shape equals to 24 minus 2 pi times 24 over 16.8 squared. So it is 24. This expression in total equals to 2 pi times 24 over 16.8 squared. In total equals to 12.823. 24 minus 12.823 equals to 11.177 square inches in size. So in total, we should hold out the area of the we are looking for this question, that is the area of this green shape. In total, it is equals to 11.177 square inches in size. Okay, thank you very much.